Question 4, Part B. A function f of x is defined by f of x equals x plus 3 in brackets times x squared minus 9 in brackets. Part 1. Find all solutions of f of x equals 0. F of x is expressed in factor form, although not fully factorized. So f of x is equal to x plus 3 in brackets times x squared minus 9 in brackets. And we want to solve f of x equals 0. In other words, x plus 3 in brackets times x squared minus 9 in brackets equals 0. Now, because it's in factor form on the left-hand side, we can use the null factor theorem. That means either x plus 3 equals 0 or x squared minus 9 equals 0. This gives rise to two cases. So case 1, x plus 3 equals 0, so x is equal to negative 3. And in case 2, x squared minus 9 equals 0. Rearranging the equation to make x squared the subject, we get x squared is equal to 9, and taking the square root of both sides, we get x is equal to plus or minus 3. Now, the solution here, minus 3, is identical to this solution here. So, combining all those solutions, we get the solution to f of x equals 0 is x is equal to negative 3, or x is equal to 3. Part 2. Find the coordinates of the turning points of the graph of y equals f of x and determine their nature. To find the x coordinates of any stationary points, we first need to differentiate f of x with respect to x and then solve the equation f dash of x equals 0. Now there's two ways we can differentiate f of x. We can expand it and then differentiate it normally, or we can apply the product rule since f of x is a product of two functions of x. I'm going to use the product rule to find the first derivative. So using the product rule, f dash of x equals u dash v plus uv dash, where u is equal to x plus 3, u dash is equal to 1, v is equal to x squared minus 9, and v dash is equal to 2x. So f dash of x is equal to x squared minus 9 plus 2x times x plus 3 in brackets. Expanding the brackets, we get f dash of x equals x squared minus 9 plus 2x squared plus 6x. And then simplifying by collecting like terms, we get f dash of x equals 3x squared plus 6x minus 9. Next, solve f dash of x equals 0. In other words, 3x squared plus 6x minus 9 equals 0. Now we can turn this non-monic quadratic equation into a monic one by dividing all terms by 3. So we get x squared plus 2x minus 3 equals 0. Factorizing the left-hand side, we get x plus 3 in brackets times x minus 1 in brackets equals 0. And using the null factor theorem, we get x equals negative 3 or x equals 1. Now I'm going to use the second derivative, f double dash of x, to determine the nature of the stationary points. So differentiating f of x, so differentiating 3x squared plus 6x minus 9 with respect to x, we get f double dash of x equals 6x plus 6. So I'm going to summarize my findings in a table of values. So our two stationary points are at x equals negative 3 and at x equals 1. We need the y values, or the function values, that correspond to negative 3 and 1. So that's why this table has 3 rows. So the value of the second derivative when x equals negative 3 is negative 12. That means it's concave down at that stationary point, which means the stationary point where x equals negative 3 is a maximum, and when x equals 1, the value of the second derivative is positive 12. That means it's concave up, which means that stationary point is a minimum. And the function values, when x equals negative 3, it's 0, and as we found in part 1, x equals negative 3 is one of the points where the graph crosses the x-axis, in other words, where f of x equals 0. And when x equals 1, the function value is negative 32. Therefore, the stationary point at negative 3, 0 is a maximum, and the stationary point at 1, negative 32 is a minimum. Part 3. Hence sketch the graph of y equals f of x, showing the turning points and the points where the curve meets the x-axis. The graph of y equals f of x is cubic since the leading term is x cubed, and we get that by multiplying the term with the highest power in the first bracket by the term with the highest power in the second bracket. So x times x squared gives us x cubed. So the graph of y equals f of x will look like a sideways S shape. Now the y-intercept of this graph we find by letting x equal 0. So f of x in this case is negative 27, and that's shown here on the graph. The x-intercepts of the graph we found in part 1, which is negative 3 and 3. So here is a sketch of the graph of y equals x plus 3 in brackets times x squared minus 9 in brackets, showing the two x-intercepts, the y-intercept, and the two stationary points at -3, 0 and 1, -32. Part 4. For what values of x is the graph of y equals f of x concave down? The graph of y equals f of x is concave down in the interval where the value of the second derivative f double dash of x is less than 0, where f double dash of x is 6x plus 6. So we need to solve the inequality 6x plus 6 less than 0. Now moving the positive 6 on the left-hand side over to the right-hand side, it becomes -6, and we don't need to flip the inequality sign around since we're not multiplying or dividing by a negative number. So we have 6x less than -6, dividing both sides of the inequality by 6, we get x less than -1. Therefore, the graph of y equals f of x is concave down in the interval x less than -1.